In previous videos, I was playing with system calls and trying to make a very the thinnest program that is possible that are still using system calls. I never went farther than Hello World, and I want to continue there because I still had a few questions remained. So I want to go as deep as possible till I convince myself that I understand what's happening, what are the pieces there. Yeah, that's one point. And the other point was that the binary which created with assembly was still over 8K long, and that is why is it so big? I mean, we had only a few instructions there, and there is the ELF binary format, and it has a header and all sections and all kinds of things. So those need some space, but what is this 8K coming from? So these were my original goals, and then I went a bit deeper. But before we go on, let's do a quick recap, so you don't have to watch all the videos. So let's create a very simple Hello World C code. Nothing interesting here, just we are printing out hello. Even if you don't know C, this is pretty readable. Let's compile it. Call it hello. Yes, it works. It printed out hello. I am a perfectionist, so let's add the new line here. Sorry about that. Okay. So what can we see about this binary we created? First of all, it is 17K long. We did not turn on any kind of optimizations. But I don't think that matters a lot here. We could let's try what happens when I add -02 -std null 17. Yeah. Well, I actually thought that this will be a bit smaller, but no, there was nothing to really optimize away. That's 303. Yeah, amazing. There is one thing that maybe you heard about. This is stripping the symbols of a binary. We can do that by sending the linker. GCC is the compiler, but GCC also links this process. We could do this in two separate ways by calling just -c and creating an object file first, and then call the linker ld on it. But the proper way, if you are using libc, is to call the linker through GCC. So what we can do, how can we send options to the linker is this with weird syntax. So the L means here linker, and what is the W? I'm not sure. Anyway, so after these 4 characters here, you can send options to the linker, and the -s means strip the symbols. If we do that, then we strip off 2K from the hello World. But then some things already doesn't work, like nm is the program that prints out the symbols. Yeah, they are gone. Of course, let's move back. So if we leave the symbols here, then we can see all the symbols here. Like here is the main function and the address in the binary for the main function. Here we see the start function, which is injected to our code. Start will do a couple of things like about the program arguments and environment variables, and I think zeroes out the BSS section. Although the kernel also does that, so I did not go deep into what the start does, but I have a vague idea. Then it will call libc start main, that will also call a few other things, and then eventually the libc start main will call main. So that's how what is the normal process in Linux. The other symbols are various segments, the BSS segment, data segment, start and end, and address, I think. Yeah, the printf turned into a puts call. This is undefined here because it is called in libc. I'm just doing a quick recap here, not going deep into it. Another thing we could look at is the readelf command. If you just want to look at the header of the readelf, then yeah, this is, I think, pretty readable. It's an elf64 binary because I'm on a 64-bit CPU. Here is the magic for the elf binary to recognize it, and we can look at the number of program headers, 13, and the section number of section headers, 31. Oh, that's now these are a lot. This is why I'm not investigating the C library at the moment. I wanted to have a very stripped down version. The shortest, smallest binary that I can create that still prints hello world. So let's not go into this one, but move to our assembly code. I will use NASM as before. Let's call it hello ESM. Let's make this label start label global, so the linker can see it. We will have two sections. Sections and segments are in the elf file are yeah. I almost said that it's the same, but that's not true. So when you have I will talk about this later. So we will have a message. We will have a data section which will contain the hello string. DB means data bytes. So we will list the bytes, consecutive bytes after each other. Hello is the string, and 10 is the ASCII new line. Then this is the address of the first instruction. Now before I write this down, I copy paste some comments here. So what the hell I'm doing here now? If you don't know assembly. So this is the calling convention of a system call on Linux. So a system call is like a function. It has a convention of where to put things to know, so that when you call the syscall instruction, after putting all these things to the right place, then the kernel will take them and know what to do. So first of all, the system call doesn't have a name. I mean, you don't send a name like a function name. It has a number, and of course in documentation and for humans it has a name. And for getting that name, you can, at least on my system, you can see this in this file. Let's quickly look at it. So here is you can see that we have a little over 400 system calls. Let's look at the top. So we will use the write system call, which is one of the main things. So read, write, open, close. These are the main Unix abstractions over many things. For example, printing on the screen, write. So the write has the number 1, and we will use another one called exit. Exit is the proper way how you can close a process, by sending also an exit value, which is the result of your process, whether it was successful or not. And if not, then you can indicate some errors. Okay, let's go back to the assembly code. So system call number will go to the RAX register. It has a maximum 6 arguments, and in this exact order. So RD registered for the first argument, RSC for the second, RDX for the third. Then you call syscall. and the return value will be in the RAX register. The system call will override it. And also, just to keep this in mind, that Syscall will change these two registers. That's how it works. I don't want to get more into that, but after a system call, you can't rely on these two values anymore. Okay, so let's quickly write our hello world in NASM, in Intel syntax. So we will move mov1 to RAX, which is the write system call. This is the write system call. Then the first argument will go to RDE, which is the file descriptor. Which is so stdin is 0, std out is 1, std error is 2. You get this for free if you start things from bash. And I think also for other programs. And we want to write out to the std out, so that's why we are sending 1. And then the second argument will go to RC index. This will be the memory address of the text. Then the last argument goes to RDX, which is the number of bytes we want to write out, which is 7. And now we can call syscall, and this will already print out the hello string, but we are not done, because then we will get back the control. The process will get back the control, and it will move to the next instruction. If you don't write any instruction here, then whatever it finds in memory there, and that will result in a seg fault, or because probably an unknown instruction got called. So now we will call another syscall, which is the exit one, which we looked up earlier. The number was 60 of that system call, and it has one argument. Again, first argument goes to the RD register, and we could do this, or we could do this. The reason why people do this in assembly is because x86 64 has variable length instructions, and this is a shorter instruction. So it's fewer bytes than moving. It just means that RD equals 0, and then we call syscall. Okay, so let's save it and let's compile it. We will create an ELF64 binary. We will call the linker after this, so we will create an object file first. asm.asm, yes, and we call the linker asm.o, and let's check whether it works. And it didn't work. Okay, what did I mess up? Okay, this took me an embarrassing amount of time to figure out. So the section data, we started a section data here for the message, but for runnable code, it goes to a different section called text. Yeah, that was a bit embarrassing. Okay. Okay, this is what I wanted to see. We can see that Hello ESM has no dynamic libraries. We can check with strace that it really calls the bare minimum. So strace will start with exeq system call our binary. Then the binary will itself call write and exit 0. That's really nice. But if you look at the size, it's what? it's not much shorter than the binary we got from the C hello world, which had a lot more symbols. So something seems off, right? I want to understand why. Okay. Yeah, we can look at it from different angles. Let's maybe start with the object dump. Just look at it. I mean there should not be not many non-zero values there. I mean this is really small. So we will use the inter syntax here. We will ask object dump to please dump us inter syntax, not AT&T syntax, which is the default. This is actually pretty nice. Okay, the code is small. We can see what it compiled. Yeah, there is not. Of course, it changed a bit because this is the small part of the RAX register, the 32-bit part, also for the RD, because you don't need to use the 64-bit value. If you just use these, then the upper half will get zeroed out. So apart from these kind of modifications, what it compiled is exactly what we wanted. So it's not in the code segment. That's what we can see here. We can do a hex dump. So let's treat this as a big blob. What is the argument for it? I think -c. Yeah, I think that's enough. So you can see the whole thing. And so here are the binary. Here is the binary, and here we can see in ASCII. And sometimes it makes sense. So like the ELF binary has this magic few bytes at the top, and it has the ELF word in it, so you can eyeball it. Also, we can see a hello here. Our string, our literal string got. This is the data section. That we can immediately see that this will be the data section because that's where we put it. And the 0a is 10. That's the new line. These look like the symbols, so the symbol table must be here. What else? Now this is interesting. This is the text segment, and we can figure this out just by eyeballing it, because we know that whatever this is, we move the RAX to the RAX register 1. We move to the next register 1. This was the file descriptor. This was the number of the system call. This was the file register. The next one is a bit messier because that was the address of a message. So there should be a 64-bit address here. So that will be long. But we can find the 7 here, which we manually typed in, which was the length of the message. And yeah, so this one repeats. So B8 looks like the move RAX, to move something to the RAX. The 3C is actually 60. So this was moving 60 to the RAX register, moving 1 to the RAX register. So we are done for this is after the Syscall. So we can figure this out just by that this is the Syscall's opcode, and here we see the second Syscall opcode after the exit. So we moved 60 to the RAX register, then we XOR the next the argument, and then we called so that must be this one. Then we called a system call. This is the text session, and in hexdump this means that there is a big blob of all zeros here. So here are the addresses. We are jumping from F0 to 1000, which is coincidentally is the page size, memory page size. Of course, that's not a coincidence. And here we can see that the text segment starts at 1000 and the data segment starts at 2000. So again, a page size. And yeah, it doesn't go to the 3000, the data segment. So something going around the page size. And if it just maybe let's look at the readelf. Let's read all the sections now, because this is a bit smaller than the hello world was in C, and maybe we can learn more things from it. So this is a more structural way to look at the bytes. What we did, we can see an entry point address. This will be the first byte of the text segment where the code runs. We can see the number of program headers is 3, and now that's much more easily to handle than 30 or 13. Number of section headers 6. That's still quite big. Yeah, we can see the section headers. So text and data. That's what I mostly care about. We can also see some flags. I forgot what the A is, but X means executable. I think this is writable. Maybe this is allocate. Maybe this signals that allocate a page for it. I'm just making this up now because I forgot. Here, alloc. Yeah, no, okay. I did not make that. All right. What else? Okay, program headers. Read executable. So yes, I think this. I think we can understand this without knowing without opening the documentation. So we saw that this was the text segment's offset in the file, and we know that the entry point is this. So this section from the file will be mapped in the virtual memory to this address. That's how we can read it. And this section from the file, which was the data segment, this is where the hello started, will be mapped to this address in the virtual memory. So this will be in 2 memory pages in the virtual memory, and one of them will be read only, not because there is no W, and executable. Makes sense. That's where our instructions are. And this one will be read and write for the data segment. I can imagine only a readable data segment as well, but this is read write. Okay, and the symbol table. We can actually strip this. So let's take a look if we. Where was it? Here. So we can call LD with -s. And let's call readelf on it again. And now we got rid of a bit of a clutter. Yeah, we have less section headers, less. No, program headers are the same, still the same. I think this is section header, this SH. The null is I think that's just an elf thing, that there must be a null one here with 0 size. No, it maps something to this address before the page. I'm not fully sure now what this is. Okay. So how can we learn a bit more here? One of them is obviously man page for the elf file. So I think this is pretty good. So for example, if you want to understand the header, then we get a C code for the header. So edent is the magic. Is the 16 bytes of magic at the top with the elf word in it. This is how you can recognize that this is really an elf binary. But there are 3 kinds of elf binaries: the relocatable files, object dynamic library, dynamically loadable, and the executable ones. I hope I said this correctly. So for example, the entry point is here, and the various number of program headers, program headers number, the section headers. We can understand the header part at least. I mean, it totally makes sense. Then we have the pointers to the sections, and the sections will probably have a header and also various flags, like please map this to an executable memory page later. Yeah, this is I think this is the file offset, and this will be the virtual address. That's how I read it. But yeah, I did not. I mean, it's just based on the name, it makes sense. So my goal is to get to the understanding where I convinced myself that I understand most of the parts here, and you know, getting to the deeper and understanding every bit is yeah, we can do that as well, but that's not my goal. I just want to convince myself that I can understand. I know enough now. But still, this is pretty long, and I challenge myself. Can you make it shorter? Oh, we can. So this is man elf is one way to read about it. But if you want the real final saying of what an elf binary looks like, the final source of truth is of course the documentation. Let me quickly show it. So the Linux ABI is split into two documentation. One of them is the System 5 ABI documentation. This is what I am showing here. So it has this is and there is a CPU specific documentation that so you have to read both. This one is a generic one which contains things that are applying to every kind of CPUs and every system, every Unix system that adheres to this, and the other one which is this is the processor specific one. In this case, this is AMD 64 architecture. And now we can, for example, in this, we can look at the object file parts, and this will just list changes or specifications of according to the other documentation. This is the generic one. And but, for example, elf header sections. So we can see here during the program loading. So why the kernel during program loading will map the parts of the file, the segments, to virtual memory segments. And for efficient mapping, executable and shared object files must have segments whose file offsets and virtual offsets are congruent to the modulo to the page size. So basically, that's the answer. That's why it is 8K, because we have a data segment and an executable text segment, and the page size is 4K, so it starts with 8K, and some extra stuff is for the elf header and symbols and whatnot. But we won't stop here. So let's go back to the terminal. There are other flags to the LD. So I will now search it directly. So I want to call out two of the. Just a moment. Here you can actually read it. So these two, the -n and -begin. So this will turn off page alignment of sections and disable linking and shared libraries. Okay, let's see what happens. The other one, set the text and data sections to be readable and writable, and also do not page align the segment. So according to the ABI documentation, it should be aligned on page, and but we can turn it off. Let's see what happens. So where was my LD line? Here. So we can do this. Let's leave the symbols in for a moment. We see that it is now half of it than before. Let's go back just for a moment so we can compare it as I'm changing things. So let's look at the symbols in it. Yeah, not much. And maybe let's look at the header only of the ELF header. So number of program headers 3, number of section headers 6. You know what? Let's look at everything. So here are the 3 program headers. This was the text section. This text section. This was the data section. As this was something null. Okay. Now that we know what we are comparing against, let's do the first step. And symbols are the same, I think. Maybe we missed one, but it looks almost the same. Now we have only 2 program headers. No, 1 program header actually, and 6 section headers. So here we can see that instead of one readable and executable and read-write but not executable memory page, we have at this file offset, we map that to this address in the virtual memory. Let's take a look at the entry point. Entry point address is not that, is this one. Yeah, I should really understand this. Does this even work? Let's call it. It still works. So the file offset 80 is mapped to here. But this doesn't have. Oh man, I read this. This is really one program header. Ah man, I just confused myself. So we have this is 2 lines. So this is the offset. This is the virtual address. And this will be the physical address. This is the file size and mem size. I read it badly. So yeah, we have only one page now at this address. You can do a hex dump on it. Let's see what changed. Where is my hex dump? Here it is. Okay, we still have 2 big zeros here. It's not big. Okay, this is just a small section. We can now see that where is the text segment? It was B8. So we see the data segment here, which is not page aligned anymore. Ah, here it is. Yeah, this is where our code starts, and this one is still. Oh no. So this is where it starts, and this is actually mapped until how far? I confused myself a bit. Oh, what I'm looking for, but are they in the same page? I mean, they should be, right? Plus 1000. Let's take a look again at the readout again. So starting from this offset, this will be mapped here. And yeah, it's a bit longer. Okay. We can do one another thing. Let's change our code a bit. So we want to understand where this is getting mapped exactly, and there is a way to see this for a running process. But for that we have to make it keep it running. So let's add another address loop here after the hello world, just to see that the code still works, and we will never exit it properly. And we will just say that please loop back there. Okay. Then we will compile it. Then we will link it, and now we will run it. Okay, it still works. Its PID is 685, and what we can do now is we can look at cat pros and maps 685 maps, and here we can see where the stack went, which address, vvor and vdso. So this one is read write, is read, and this is executable read and executable. But this is the VDSO. I don't even see. Man, again I read it badly. So this is, we have four pages, not three. These were just we got those for free from the kernel, for the program loader. So we can see that this is mapped here. We have a single page. No, this is not a single. This is 2 pages. Okay, now I understand. So this is a single mapping, but 2 pages. So that's my problem was that the text section and the data section did not correctly fit into one page. So there was an overlap, but it did not fit in there based on the addresses, and now I understand why. So we actually have a single mapping, but it is 2 pages long. Okay, let's kill this one. That was 685, and let's try the other linker option now. Okay, and now let's start it. No, let's kill it. Before we do that, let's take a look what changed. Now, if you remember, this other option did an extra thing. It also made all the pages executable, and let's take a look at it again. So this just turned off page alignment of sections. That's all it said, and then it says that said text and data section to be readable and writable, which is strange because this one already did it. Anyway, I can only read what it says here. Okay, let's run it in the same way. 719, and let's take a look at the mapping of it. So this is, we have again four mappings, and now we have only one page: read, write, executable, and private. I don't know exactly why the -n flag on didn't do this exactly. Never mind. So what changed? So we can see we have still 1 program header, still 6 section headers. It starts at 80 from the file. It is being mapped to this address. Yeah, and read, write, executable. If you look at with hex dump, we can, okay, this is the header, the elf header, because this is the 64 bytes, I think. Here we can see the the data segment, and this is the text segment. They are absolutely pretty close to each other. 0f05. Yeah, this was the second syscall, which we never get that far because we kill it. Okay, by the way, these numbers, how you can find out what they are if you are eyeballing opcode. Well, you can look at it from the Intel manuals, although that's not super simple to find. So this is the 5,000 page long Intel manual, and in the second volume there is something called opcode map and opcode tables, and we know that we are basically looking for that is B8 the mov instruction, and yeah, you have to go through this how to read them, and I'm waiting for the tables, opcode tables for 1, 2, 3 bytes opcode tables, because it has variable bytes. B8. Yeah, so here is the B, here is the 8, and this whole line is mov immediate word or doubler into word, doubler or quad register. That's what we called. Yeah, I just wanted to quickly show this. Another thing I wanted to show is that how this looks in Linux. So the program loader itself. So it is in this file called in fs and bin fmt underscore elf.c. So this file is the whole, has the whole logic for loading up an elf binary. So it starts in this line, load elf binary, and I mean this is just it's not the implementation. This was just a declaration. Here. And you can read, for example, the comments if you just quickly want to go over it. And at some moment when I was searching for this and understanding why it is being, how can a small binary work if it has to be m-mapped? And I was searching that, are we really always m-mapping? And yes, we always m-map. So that was my point to find here. Let me find some place where we can have some takeaway here. Here, this line. So now we do a little cranky work by m-mapping the elf image into the correct location in memory. And you can follow this code. It's mostly self-contained. Yeah, I just wanted to show. I will send a link to below the video. Here is an interesting one. So this is one of the loops, and so this logic is run once for the first load program header for the executable binaries, which is our case now. We have an executable binary, and it will call mmap with this map fixed no replace. And for example, you can look at what this does. So it tries to, it's similar to map fixed. It tries to map something to the address that you wanted to. And the map fixed has some issues that it actually can screw up previous mappings, and this flag doesn't do that, and so you will get a proper error if it would screw up other mappings. So you can basically, which I didn't know before, that you can take offsets from the file and map them to different direction in virtual memory, and add different flags to those mappings, like this is executable, that one is not executable. Why we don't get such a binary by default from the linker, I'm not sure. I mean, it feels like, this is a micro optimization, so what's the point of it? But it's still a bit weird, because if you can do it, why not? Why have an 8K file if you don't have to have it? Okay, I think I will stop here. We learned a bit more, bit deeper about the ELF binaries, and I think I gave a few pointers if you want to dig deeper than this. Thanks for listening. Bye bye.